Hello, my name is Daniel Schwartz, and today I'll be presenting on fusion learning on multiple-tag RFID measurements for respiratory rate monitoring. Many current techniques for respiratory monitoring and ventilation devices are quite invasive, requiring a patient to be tethered to cables and devices. To address this, we propose improving upon a non-invasive device that captures respiratory activity with radiofrequency identification technology. Our goal is to have our non-invasive device operate at a standard comparable to medical devices currently used in hospitals. The device we use is called the BIBE, a wearable smart garment that enables continuous monitoring of a patient's respiratory activity. The BIBE is composed of three main components, the first of which is a stretchable conductive fabric that acts as an antenna, identified on the image on the right by the gold area. The second important part is the RFID chip sewn into the fabric, which is identified by the blue area on the graphic. Finally, the belly band is fastened with a Velcro strap on the back. The patient wears the belly band around their abdomen or waist. When the patient breathes, there are two signals that occur in the belly band. The first of which is that the fiber antenna structure changes in both shape and size, and then the second change is the general location of the antenna also changes. These changes cause alterations in the signal, the received signal strength indicator RSSI, from the belly band, and then from these alterations we can infer respiratory activity. Radio frequency identification, or RFID, is a wireless communication that uses radio waves to track an object. There are some advantages to using RFID technology, such that it is powerless, thus there are no wires or batteries necessary. It is also sensitive to fine movements and less affected by gross movements. However, there are some challenges to using RFID, such as channel hopping, signal strength decay, reflection, absorption, and multipath fading. Many of these issues have already been addressed in previous work using a single tag. However, noise artifacts from multipath fading are still present in the signal received from a single tag. The wearer can still introduce non-respiratory movement. So, to combat this, we time synchronize the belly band with a reference antenna that is attached to a relatively stationary part of the body. So as you can see here in the graphic on the right, the belly band is on the right on the chest, where the reference tag is further up, closer to the shoulder. Now on a baby this is quite hard because it's such a small surface area, but on a larger human you can imagine on the shoulder and on the chest, two different locations. And then from these two signals, we use our sensor fusion algorithm that we developed that can infer respiratory biosignals more accurately with the use of this reference tag. Our approach has 5 main steps. The first is that we input 2 radio frequency channels. One is the signal from the belly band, and the other is the signal from the reference antenna. Using a complement of a switching regime hidden Markov model, as well as a Markov chain Monte Carlo and a z-test, we then separate each signal into 2 states. From that, we sample a desired state from each signal using a sliding window process. And then from the resulted window distributions, we extract a Minkowski distance between the components of both the RF signals as a higher order feature. Finally, we fuse the resulting signals using Mahalanobis distance measure. For the experiment, we quantify the improvement in signal quality by calculating the signal-to-noise ratio of both the input and output signals and compare the two. Thus, an increase in SNR without loss of spectral centroid power implies that we have a denoised signal. As you can see here, here's almost a process flow diagram of how our algorithm works. We take the data from the belly band, which is in blue, and the reference tag, which is in red, throw it through a regime hidden Markov model and a Markov chain Monte Carlo to then create these 2 different states, where the red is indicating a fixed relaxed state and the blue is a stretching state. From there, we take a z-test to further clarify the 2 different distributions and then pass this through a sliding window Minkowski distance to get these features, such as RSSI, velocity, and Minkowski distance, and then pass that through Mahalanobis distance to get the fuse signal that originated from both the belly band and the reference tag signals in the beginning to get an actual accurate depiction of the breathing rate. For the regime hidden Markov model, we use a semi-unsupervised approach, training the model with 30 seconds of data that contains a known respiratory rate. The trained model then classifies each subsequent point as belonging to one of 2 hidden states. Then, we perform a metropolis random walk with a Markov chain Monte Carlo to further refine the distributions of these 2 predicted states. Finally, with the z-test, we separate each signal into these two states. For the main antenna, the two states are stretching and fixed relaxed, and then for the reference antenna, the two states are coupled and non-coupled. And from there, we get this graph of the two different states, fixed relaxed and stretching, to see the difference of the state separation within the main antenna signal. We ignore the fixed relaxed state of the main antenna and the coupled state of the reference antenna. Thus, we then sample the stretching and non-coupled states of the antennas using a sliding window. The signal is normalized, so this also has the potential to remove mechanical effects like a person ambulatory during monitoring. The sliding window is parameterized with a length proportional to the breathing rate and a stride that's 1/4 of the window's length. For a rate of 15 breaths per minute, the window length would be 2 seconds and the stride would be half a second. Calculating the Mahalanobis distance between time-synchronized windows at this point can cause the algorithm to fail. This is due to the presence of a low-resolution signal where the distributions in the two windows can have a high covariance with each other and thus generate a singular covariance matrix. In order to reduce covariance, we measure a Minkowski distance between the signal strength and velocity components of each window and extract it as a higher-order feature. And the Minkowski distance is essentially just a metric in a normed vector space, which is a generalization of both the Euclidean and Manhattan distance with a different higher order. After increasing the dimensionality of the windowed signals and decreasing their covariance, we then fuse the two signals together with the Mahalanobis distance. We take the Euclidean distance of the output's matrix's diagonal to find the number of standard deviations each window is from its time-synchronized counterpart. A low deviation implies the signal from the bellyband and reference antenna are both similar. Meanwhile, a high deviation implies that they are different. So as you can see here, the bellyband is in blue and the reference tag is in red. And after computing the Mahalanobis distance of these two different signals, we get this purple graph, which shows the Mahalanobis distance from each other. To calculate signal-to-noise ratio, we then locate the input and output signal of spectral centroids identified by SC by taking a weighted average of the 3 frequency bins adjacent to the known respiratory rate. The spectral centroid's power is then found with linear interpolation. We're able to subtract this from the average magnitude of all other frequency bins to find the overall signal-to-noise ratio, referred to as SNR. For experimentation, we use a wireless channel emulation that provides a mechanism for evaluating wireless links in both a controllable and repeatable manner. We then use a custom PCB, which is developed to interface with commercial passive RFID chips and commercial wireless channel emulation. This wireless signal model can be used to create synthetic channels, which is representative of an on-body RFID propagation environment. This overall structure is used with the Echo Ridge dynamic spectrum environment. And as you can see here, the graphic on the right at the top shows the board that we use that has a Monza R6 chip, and then the flow diagram shows the RFID router, which is divided into by a power divider that has both a dice channel 1 and dice channel 2, and we have the two different emulation boards with the RFID chips on each. And the green is a reverse path, while the red is a forward path. With the dice, we generate one reference and two main signals that contains a respiratory rate of 0, 15, and 30 breaths per minute respectively. Thus, for us to create a robust dataset, we iteratively transform these signals by adding a point randomly sampled from a Rayleigh distribution that is parameterized by the original signal's features. This point is normalized using the mean of the Rayleigh distribution and multiplied by a scalar noise factor to introduce more variability into the dataset. So in this flow diagram here, we have the main antenna signal and the reference antenna signal. Each pass through a Rayleigh fading model and then get that faded signal, and the faded signal before is from the main antenna and the faded signal after. And we take the Mahalanobis algorithm and we then compute the signal-to-noise ratio from that. This is an example of one of the trials with the graphic to the right. The input signal in blue has a breathing rate of 30 breaths per minute, a window size of 1 second, and a window stride of 1/4 second, with a noise scale of 3. The transform signal in red represents the similarity of the input signals from the main and reference antennas interpreted in decibels. Looking at each signal's Fourier transform below, you can see an increase in the power of the spectral centroid highlighted in red and a decrease in high-frequency artifacts above 1 Hz. For this signal, the input spectral centroid power is negative 13.29 decibels, and its output power is negative 6.84 decibels. Now this table below displays average values across all 120 datasets. Each row represents the average values from 20 trials for each noise scale C. As the noise scale increases, more high-frequency artifacts are present in the signal that are removed by our denoising algorithm. This results in an increase in the change in SNR, which is seen in the farthest right column. Overall, the average input SNR is 17.12 decibels, and the average output SNR is 34.74 decibels. This is an average improvement of over 17.62 decibels. In conclusion, this algorithm fuses two RFID signals to remove multipath fading and temporal artifacts. One signal from the belly band transmits respiratory biosignals and the other a stationary reference signal. RFID signals are emulated using the dynamic spectrum environment, DICE, and Rayleigh fading. Signal-to-noise ratio is leveraged to quantify the improvement in biosignal quality. For future work, we will adaptively parameterize the sliding window in response to changes in respiratory rate. Also, we will build a machine learning framework that can be used for respiratory artifact detection. Ultimately, we hope to orchestrate these tools with the belly band to provide predictive ventilation in dynamic life support systems. Thank you.